So today we are going to start to finish up section 2. Today we're going to learn how to simplify radicals. So if you took geometry honors here at McCarthy, we required you to write all of your answers in simplest radical form. So if it's not a perfect square, we need to learn how to break that down. And that's what we're going to review today. So here we're going to be simplifying radicals. So what we're going to do in order to simplify radicals, we could use a factor tree to simplify. So just remember, when the index of a radical is a 2, then what you're going to try to do is find a number times itself that would give you that number. Whenever you have two radicals and you're multiplying them, you're just going to multiply the two radicals together. The index has to be the same number. Same thing when you divide. Now, when I refer to an index, what I'm referring to is this little number that would be, for example, right here. So if there's a 3 here, then what I'm expecting you to do is find like a cube root. And we were practicing doing that. Now, we've already seen the perfect squares and the perfect cubes. Now what we're going to see is non-perfect squares. So, for example, on this 20, here's how we could break this down, because we're not going to just pull out our calculator and do the square root of 20. What we're going to need to do is do a factor tree for 20. So over here, I'm going to break down the square root of 20. Now, what I like to do is when I start my factor tree, I like to try to find a factor that's a perfect square. So for example, if I were to break down 20, I would choose 4 times 5, because I know that 4 is a perfect square. Now, some of you are going to be really good at this, and you're going to be able to find the largest perfect square that's also a factor. And then if you realize that 4 is a perfect square, you could square root it, and 5's not perfect, so you leave it underneath. Now, just to show you that you don't need to pick a perfect square as a factor, I could have also started with 2 times 10. However, 2 and 10 are not perfect. So when this occurs, what you're going to do is keep breaking it down until you have all prime factors. So 2 is prime. I'm just going to bring it straight down. And then 10 is not prime. I need to break it down into 2 times 5. Now that I have prime factors, now I go back and I look for pairs. So notice I've got a pair of 2's. Soon as you can pair up two square roots, that becomes a perfect square. Now, I don't need to worry about multiplying 2 times 2 and get the square root of 4. I just take out the number that's under both of the radicals, and now it's freed up. Because if I were to multiply it back, I would get the square root of 4, and then I square root that 4, and it turns into a 2. There is nothing to pair up with the 5, so I leave him under the radical. Now, if you end up finding a number that there's more than one pair, then you'll pull out as many pairs as you can make. Like, for example, let's say we wanted to do 48. So, for those of you who are good, again, at finding factors that are perfect squares, I could break 48 into 16 times 3. And then if you recognize that 16 is a perfect square, square root it and leave the 3 underneath. But let's say instead, I'm like, I don't want to do that. I want to do 2 times 24. So when this occurs, what you're going to need to do now is keep breaking it down till it's prime and then look for pairs. So for example, 2 is prime, 24 is not. I need to keep breaking 24 down. So I could break 24 into 2 times 12, 3 times 8, 4 times 6. Let me go ahead and do that one. I still don't have prime numbers. I need to still break down the 4 and the 6. So break down the 2, break the 4 into 2 and 2. Now, if you realize 4 was a perfect square, you could square root it as well. Now that I have all prime numbers, now I'm going to go and look for pairs. I've got a pair of 2's, so I take out the 2 out of the radical. I've got another pair of 2's. I take a 2 out of that radical, and then now the 3 has nothing to pair with. He stays underneath. Everything that came out, I multiply back together, and then I leave the 3 underneath. Notice it was the same answer as starting out with 16 times 3. Again, it doesn't matter what that first row of factors, if it's not a perfect square right off the beginning, keep breaking it down till it's prime. Even if you would have started with the 16 times 3, and let's say you didn't know 16 was a perfect square, then you got to break it down. And then as soon as you see you got a pair, you could stop here, pull the 4 out, and get the 3. Wherever you're comfortable doing, but we're going to be leaving our answers in simplest radical form. We will not be using a calculator. And then here, just to clarify, whenever you multiply 2 radicals, they have to have the same index. So let's say I said to find the cube root and multiply these, and see how the indexes here are little 3's. Whenever you do something like that, you can multiply these 2 together, but then it keeps the same index. This couldn't be broken down, so I would leave it just like this. Same thing if it were a square root. When you go to divide radicals, so for example, the one at the bottom, the square root of 10 divided by the square root of 5. Because both of these are under a radical, I'm going to do 10 divided by 5. I get 2, but it stays under the radical. I can't simplify the square root of 2. It's in simplest radical form. So now we're just going to do a whole bunch of examples practicing these rules. Let's try our first example. Oh, and notice I did 48, but I'm going to do different factors for that one. All right, so 28. So again, you can go about this whatever 2 factors you want to start with. So again, if you're good with recognizing that a factor of 28 is 4, and 4 is a perfect square, and you realize that, you could just go right into square root of 4 is 2, 7's not perfect, I can't break it down, it's prime, and you're done. But let's say instead you decided, you know what, I want to do, for 28, I want to do 2 times 14. Just to show you, it doesn't matter, just looking for 2 numbers that'll multiply to give you that number. 2 is prime, 14 is not. Keep breaking it down. Now go back, look for pairs. I've got a pair of 2's. 2 comes out, 7 stays underneath. Same answer I got when I started with 4 times 7. Now the second example, 48. I already did 16 times 3, and I did 2 times 24. What if we did 4 times 12 instead? Again, if you recognize 4 is a perfect square, you could pull it out, but let's just go ahead and bring it all the way down to prime. So 4 would become 2 and 2. 12, I could either choose to do 2 and 6, or I could do 3 and 4. It doesn't matter. So let's say I do 3 times 4. I'm still not at prime. The 4 still needs to keep going. These are all prime. I'm just going to bring them down so they're all on the same row here. And now I've got all prime factors. Go back, look for pairs. Pair twos, pair twos. 2 comes out of each of the pairs. 3 stays underneath. And then go back and multiply the 2 that came out. Same thing would happen. Let's say I said instead, I want to do 6 times 8 is 48. Again, you're going to break it down till it's prime because neither of these numbers are perfect squares. Break it down to 2 times 3. Break the 8 into 2 times 4. And again, 4 is still not perfect. Well, 4 is perfect, so I could pull it out, bring everything else down, and now go look for pairs. Let me separate that. So I got a pair of 2s. These, even though they're not side by side, they pair up. So a 2 comes out of that one, 2 comes out of that one, and then the 3 didn't have a pair. Now, if you have more than one number that's not a pair, you would multiply that back as well. And we'll see this coming up. Now, next example, it's got a 2 outside of the 48. Well, I already did 48 a whole bunch of times. So I already broke it down, and I knew 48 breaks down into 4 square root 3. But we still have this 2 that was out here to begin with. So now anything that comes out of the radical, that's a perfect square out of the 48, is going to get multiplied to that 2 that was originally out there. So this would give you 8 square root 3. Going to do the same thing on number 4. I need to break down the 45. So the 45, the only way that I know to multiply it besides 1 times 45 is 9 times 5. Actually, I could go 3, but we're going to do 9 times 5. This 6 was already out here. So let me just stick him out here. So now, if you realize 9 is a perfect square, you could just square root it and make it a 3. Or if you're not sure, let's break him down. He's 3 and 3. And then the 5. And then the 6 that was still out there. Now that I have prime factors under those radicals, make your pairs. Pair of 3s. 3 comes out. He's going to get multiplied to the 6 that was originally out. And leave the 5 underneath. So 6 times 3, final answer here is 18 square root 5. Example 5, we've got a 14 outside of the radical and a 75 inside. So the 14 is going to stay outside. But now I got to break down the 75. I could choose to do 5 times 15, but I'm going to do 3 times 25. When I see 75, I think about 3/4. So 25 times 3 will give me 75. And again, if you're good and you recognize 25 is a perfect square, you could square root it right here and now. But I'm going to break it down just to show you the technique of getting it all the way to prime. And then the 14 was still outside. Make your pairs. I got a pair of 5s. 5 comes out. It's going to get multiplied to that 14 that was already outside. And then 14 times 5 is 70. And then the square root of 3 stays behind. For number 6, I need to break down the 125. Again, I'm going to think about quarters. $1.25 to me is 5 quarters. So I'm going to break 125 into 5 times 25. The 10 was already outside. So now just to show you, for those of you who are going to automatically start with the largest perfect square as a factor, I don't have to actually go all the way to prime. I could square root that 25, leave the 5, this 5 underneath, the 10 was already out, and now go back and multiply everything that came out and leave the 5 underneath. We're going to do this so often that you're going to be able to look at these numbers and automatically know what that largest perfect square is, and then not have to take it all the way down to prime. Pretty good? Let's try another one. We're just doing lots of practice here. Number 7. Again, lots of factors of 600, but I'm going to again try to find the largest perfect square, and that's going to be 100. So I'm going to break 600 into 100 times 6. Now, again, if you're not sure and you want to break down the 100, you could keep factoring that as well. But again, if you're good, this would become 10. 6 stays underneath. Can't break it. You can break it down, but there wouldn't be any perfect squares hiding. And we would get 50 square root 6. Let me go ahead and do all the way down just to show you. Let me do it again. So 5 and then the 600. Let me take it all the way to prime, just in case you didn't recognize those perfect squares. So again, I'm going to still do the same one, 5, and then this will become 100 times 6. But let's say you wanted to break it down. So the 100 becomes, I could do 10 times 10. I could have done 4 times 25. The 6, I'm going to make it 2 and 3. The 10 becomes 2 and 5. This 10 becomes 2 and 5. And then the 6, bring down that 2 and 3 that you broke down. So now go back, look for pairs. Pair of 5s. 5 comes out. Got a pair of 2s here. A 2 comes out. This 5 was already out. And then notice now, and we haven't seen this yet, but notice on this 2 and 3 here, notice there were no pairs for it. So when you have a radical underneath that's left behind that doesn't have a match or a pair, you just multiply those back and turn it back into a 6. Now I'll go back through and multiply everything that came out. So 5 times 5, 25 times 2, or 5 times 2 is 10, times 5 is 50. So 50 radical 6. Same thing I got when I recognized that the 100 was the perfect square, and I made it the 10, and then I recognized that 6 I knew only had a 2 and a 3 in it, and I couldn't break it down. Let's try example 8. Now, here's where we're multiplying. When we multiply two square roots, or numbers that have square roots, I can only multiply numbers that are outside the radical together and then numbers inside the radical together. So what I would be doing here is multiplying the 5 times 2 and get 10, and then I would multiply the 3 times 3. Now, you can either multiply it and get square root of 9, and then you have to square root it, or realize, hey, when I multiply 3 and 3, I really got a pair of 3s. So what comes out of here is a 3, and then you'll multiply and get 30. If you didn't recognize that, you would do the 2 outside numbers, but then the 2 inside would give you square root 9, but then you have to square root it, and you still get to what we got there. So whenever you see 2 radicals and they're exactly the same, don't bother multiplying them, just take away the radical symbol and write the number once. Let's try some more examples. Number 9. Now, again, we can go about doing this problem 2 different ways. Because we're not using a calculator, what I recommend you do is don't multiply the three numbers under the radicals. So you can multiply 5 times 5, get 25, 225, 25, and then multiply that by 9, and then get 225. But then you still got to go back now and break it back down again. So you're better off leaving it and then breaking down the numbers the way they are. Now 225 is actually a perfect square. It's 15 times 15. But the way that I recommend you do it instead is, let's rewrite the problem. Instead of multiplying 5 times 5 times 9, start by breaking down the numbers before they're multiplied. Or if you see pairs, pair them up and take it out of the radical. So for example, pair 5s, this tells me this 5 comes out. And then if you recognize 9's a perfect square, square root it, and boom, it goes to the same answer as going through the process of doing 5 times 5, 25, times 9 is 225. So my advice to you is don't multiply those three numbers, just break it down the way that they're given. Same thing on the next one. Instead of multiplying 11 times 44 and then getting 484 and then have to go back and break it down, factor these as is. This is prime. This one can be broken into 4 times 11. And notice now I got a pair of 11s. The 11 comes out. And then the 4 is a perfect square. A 2 will come out. So my answer here is 22. 484, this number I got when I multiplied 11 times 14 is a perfect square. The square root of 484 is 22. But honestly, you don't want to have to go back and factor it. It's already started to be factored for you. Just keep going from where the problem starts. Let's try number 11. Again, I'm not going to multiply 11 times 33 and then get 363 and then have to break it down. Instead, start with this. It's prime, bring it down. This one's not prime. I could make it 11 times 3. Got a pair of 11s. It comes out. The 3 stays underneath. So the square root of 363 is 11 square root 3. It makes it so much easier if you don't go through the process, because again, we're not using calculators. So it's better if you factor the way it's given. Let's try number 12. Now we've got the division. Now, whenever you're dividing, you can only simplify numbers under the radical with another number under the radical. Or if it's outside, you can do outside with outside. So I could actually simplify the square root of 7 over the square root of 35 and make this, I can divide them both by 7, and I can make this square root of 1 over the square root of 5. I'm dividing them both by 7, and I end up with this. So once I do that, I have 6 square root 1 over square root 5. I can square root the 1. The square root of 1 is 1. So now I'm left with 6 over the square root of 5. Now, if you remember back from your Algebra 1 days or even your pre-algebra days, there's a rule that states you can never ever leave a square root in the denominator or the bottom of a fraction. We have to use a technique called rationalizing the denominator. And what I'm doing here is trying to make that denominator a perfect square so that it disappears. The easiest way to turn the square root of 5 into a perfect square is just multiply it by itself. So if I multiply both the numerator and the denominator by square root of 5, notice I've just made a pair of 5s in the denominator. So the 5 radical, it comes out of the radical, and then the top, the 6 is outside, the 5 is inside. So final answer here is 6 on the outside, 5 on the inside. Notice this square root 5 over square root 5 that I just multiplied that answer by. Technically, this is equivalent to 1. So really, all I did was multiply this white fraction here, the 6 over the square root of 5 by a 1. But it does, modify it, and it eliminates the radical from the denominator. So always remember, you can never ever leave a square root in the bottom of a fraction. Let's go ahead and try another example. So again, I am going to go ahead and try and simplify 48 over 39 first. Only what's under the radical. I can divide them both by 3. So once I divide them by 3, this now gives me the square root of 16 over the square root of 13. So now, if I put it back up here, I now have 5 square root 16 over square root 13. Notice the 16 is a perfect square. I can square root it, and now it becomes 5 times 4 over square root 13. I'm going to go ahead and multiply 5 times 4, and now have 20 over the square root of 13. Again, we can never ever leave a square root in the denominator, so again we need to rationalize. So in order to rationalize, I multiply both the numerator and the denominator by that bottom square root. Once I multiply it, notice the denominator now has a pair of 13s. The 13 comes out. For the numerator, the 20 is outside, the 13's inside. I cannot multiply an outside number with an inside, so I just write them side by side. Good? All right, let me try a couple more, and then I will finish the notes tomorrow. Keep going, do a couple more. So for 14, I'm now multiplying a radical times a binomial. So here, I'm going to apply my distributive property. So I'm going to distribute the square root of 5 to the square root of 5. Notice you got a pair of 5s. So the 5 comes out. And then when I distribute the square root of 5 to the negative 2, the negative 2 is out of a radical. The 5 is under, so I just write them side by side. I cannot combine the 5 and the 2 because in order to add radicals, they both need the same radical. So this would be my simplified answer. I think what I'm going to do is I'm going to start with number 15 because 15 is going to take me quite a bit of time and I only have 2 minutes. So tomorrow I will start with number 15 and I will finish up the notes. Now we've probably done enough where you could start the homework tonight.